We have already been able to establish that our rock, for example, a porous rock, has got three phases where we can have the solids particles within the soil sample or the rock. Then we also have got the water, that is if it has got liquid in it. And then we also have the empty spaces, which is sometimes occupied by air or any gas for that matter that may be present. So for us to be able to do some computation regarding some of these phase constituents within either a porous rock or a given soil sample, for this we need to understand some fundamental definitions. We have to understand that there is a term, mass, which is the measure of a body's inertia or its quantity of matter, and usually does not change irrespective of one's location in the universe. And then when I know of this mass, which is the body's inertia, and I multiply this by what we term as the acceleration due to gravity, I am going to have what we term as the weight of that particular body or object we are referring to. And so for that purpose, we need to understand from just these two definitions of what we have discussed earlier that I need mass, and then when I multiply that by the gravity, I get what we term as the weight of any given sample, a given rock sample or a given soil sample. And so we need to understand that this is a constant which we know from our basic education, that it is what, 9.81 meters per second square, or sometimes you may have it as 9.807. Okay, other times too, we can round it up to give you 10 meters per second square. So one should take note of these. Then we know density, being you trying to find how dense your given sample is. So you need to know the mass, which is the body's inertia or the quantity of the matter with respect to the volume it is able to occupy. And that will give me what we term as density of the given sample. So once I know this, there is another system that we need to know, or unit that we need to consider, which is termed as the unit weight of any given material. So if I have any given material and I want to calculate the weight of that sample with respect to volume, so you people usually or other books will refer to it as the weight density. So it's a form of you trying to measure the density of a sample, but this time around you are checking that density with respect to volume. So you have gotten your mass, which you know, and you multiply that by gravity, giving you what we term as the weight of the sample. And having known the weight of the sample, you divide that by the volume it's able to occupy, the unit weight or the unit volume it's able to occupy. And that this expression or this particular unit of measure is usually used when we want to do a lot of civil engineering, and sometimes even if you want to consider the material, as in situ. So then that is expressed as what? The unit weight is equal to your density of the sample times the acceleration due to gravity. So take note of this as well. So unit weight is frequently used in geotechnical engineering than density, because this we are actually dealing with the weight or heaviness of the sample. Okay, we want to find out the pressure some material is exerting on a given location. For example, I want to find out how heavy a building is or how heavy material is sitting on your stove. If I want to know this, then I would like to use the unit weight as my measurement to check the weight of a material rather than using the denseness of the material, which is density. So then these have got various SI units that you need to take note of. So density of a material is known as the kilogram per meter cube. And then you have got that of Newton. The SI unit for force, which we will be dealing with it a lot of times, is Newton. And therefore we can calculate our unit weight of samples to give us what kilonewtons per meter cube, because we have expressed that our density multiplied by our gravity is termed to be what? Weight. And then if I have that over volume, so this is taking care of that of the meters cube, and then the weight is considered for the kilonewtons, which is kind of a force. So then, whilst we have gotten these, we need to understand that there is a particular standard or material in the universe that is the same, or everyone is familiar with that material, and that is what? Water. Water is a fluid that we are familiar with all over the world, such that its properties does not change. And for that reason, we want to compare some of these parameters that we usually will be dealing with respect to water. And so if I want to check the density, the unit weight of a material with respect to water, then soil. So for example, if I have the unit weight of a material and I want to obtain its density, I can use this expression. But then we should be mindful of some of the weight of water, which does not change, the density of water, which does not change with respect to a particular location, specifically at the temperature of 4 degrees Celsius, which we have to take note of. So then the unit weight of a material, if we want to convert or determine the unit weight of water, then we have already established that the unit weight of, or the density of water is this, isn't it? So if we know the density of water to be 1 gram per centimeter cube or 1,000 kilograms per meter cube, then we can easily find its unit weight to be what? 9.81 kilonewtons per meter cube. So then if I have my soil or rock, which is porous, a porous rock, then usually we will have this deposit will contain certain solid particles plus empty spaces, and then between these empty spaces I may have it being filled with water or air. And when I have all these three items, so such as having the sample and I've got section of it filled with water, so we assume this place is water, or basically saying that I have water. So if I have this as water and I have this as the void space and this as my solid particles, so I have what we term as what? The three-phase diagram, or the three-phase system of either a porous rock or a soil sample. So this is a typical picture of how a given soil sample or a porous rock may be. And then within this soil sample, I will have all of these parameters, the solid particles, the void spaces that contain air, and then my water. And this is a typical behavior of a three-phase system of any soil sample or rock. And so the three-phase, I have this as my sample, and I've got the blue sections representing that of my water, the blue sections representing that of the water, and then the rest are shown as one can observe. So, and then I have the solid state, and finally my air. When it is fully saturated, meaning that the soil sample, all the voids, you see we had something of this sort. So all the voids within, in the first instance, we had two systems. So the three systems, we have the air here, the water, and then we had the solid. But situations where you have all the empty spaces being filled with water, then it becomes a two-phase system. And so we say the sample is fully saturated with water. And so it becomes a two-phase system. Then again, you can have a situation where you dry the sample thoroughly such that all water content within it are lost. And so you have a two-phase system again, but then again, it is just air and that of solid. So this is the phase diagram. And we said that with the phase diagram, we have got the left section of it, which is this side, and the right section. The left section is usually used for finding the weight or mass relationships of the soil or the rock sample. And then you have got the other, which is the right section, signifying the volumes. So if I have any given sample, and with this sample, I have got a section. So from, let's say the whole of this is a container that contains a sample, or that's a sample. So with that sample, and assuming it is possible for one to separate the water, the solids, and then the empty spaces, you are able to arrange them neatly such that you have got them distinct like this. Then the entire sample, you have what we term as the total mass or the total weight of the material, WT here. Then we have got the weight of the solids. So that is if I were to pick only the solid section and place on a scale, I will know its weight. Then I have got, so that is what we term as the WS. Then I have the weight of the water. So if I were to pick or extract just the water alone to put on a scale, I can measure that quantity of water as well. And that is WW. Then, because this is air and it's hard for us to identify its weight, we usually will approximate the weight of air to be 0. And that of the volume, the entire material placed on inside the cylinder or any container that will help us measure its volume. When we do that, we term that as the total volume, VT. And then we have got what we term as then the volume of voids, where the volume of voids is representing the volume that is being occupied by the air and the volume occupied by the water. Remember that initially the soil or the rock sample had solid particles and that of void or empty spaces. And these empty spaces, we said, can be filled with water or filled with air. And so when I have these two things, air and water, all within the sample, then I call the empty spaces or the spots that is occupied by air as VA, volume of the air. The volume of water, VW. Then these two, volume of air and that of the volume of water, are together called volume of voids, which is this. And so that is VV. And then we have got the volume of the solid particles within the sample itself.